Okay, so now let's describe the EM algorithm. The input to the algorithm is a training corpus consisting of sentence pairs. FK is the kth French sentence, EK is the kth English sentence. And in the initialization step, we're going to initialize our T and Q parameters to some initial value. You might, for example, choose random initial values for these parameters. Then the algorithm proceeds as follows. So we take capital S iterations over the data. And as I said before, S might be typically 10 to 20 for training these IBM models. Okay. At each iteration, we first set all of our counts equal to 0. At the end of the iteration, we're going to recalculate the T and Q parameters based on the counts that we calculate. And in this middle portion, I'm going to describe how the counts are actually calculated. Okay, so we initially set the counts equal to 0, and then again we pass over every training example. So we might find an example like the one I showed you before. And we consider every position in the French string and every position paired, we consider every position in the French string paired with every possible position in the English string. So we have a loop over I and j. And then again we have these updates to our counts, which are actually identical to the algorithm I showed you previously. So we have updates where we have C equals C plus delta. The critical difference is in how these deltas are calculated. So again, remember that before we had delta kij is equal to 1 if a ki equals j, 0 otherwise. So in the very lucky scenario where we have alignments, we can fill in these deltas as either 1 or 0 depending on whether the alignment is in our training data or not. Of course, in the EM algorithm, we're not going to assume we have alignments, and so instead we calculate these delta values based on our current parameters. So I have an expression here based on the Q's and T's from our previous iteration. Okay, so the Q's and T's are our current parameter values. We're going to be able to calculate these deltas using this expression here, which I'll describe on the next slide, and we can use these deltas to increment these counts. Okay, so let's describe how to calculate these deltas using the expression I showed you on the previous slide. And to illustrate this expression, I'm going to use a particular example. So let's consider the third French word, A. So let's number these 1, 2, 3, 4, 5, 6, 7. And we have 1, 2, 3, 4, 5, 6 on the English side. And let's first consider delta 100. So this is the 100th training example. That's what this 100 here means. And I'm going to consider position 3. And let's first consider value 0, which intuitively corresponds to this word A being aligned to the null word, which is word 0. So what does this expression say? Well, on the numerator, I multiply two things together. Firstly, I have Q of 0 given 3, 6, 7. That's because I'm aligning word 3 in the French to word 0 in the English. That's what I'm considering. And then I have a T term, which is T of A given null. So that's the numerator. So basically I'm considering this alignment to null, and I'm multiplying together the associated distortion parameter and also the translation parameter. So now look at the denominator. So this whole thing is going to be divided by some expression star. Let me write star over here. So star is actually going to be a sum of terms where we're going to consider each of these possible English positions. And so this is actually going to be Q of 0 given 3, 6, 7 times T of A given null plus Q of 1 given 367 times T of A given and. So this is position 1 in the English. I have a distortion parameter and a translation parameter, plus Q of 2 given 367 times T of A given there. And I'm basically going to go through all possible English words multiplying in a Q and a T parameter, and that's how I calculate this denominator. So the denominator is essentially going to be a normalization constant, as we'll see very soon. Similarly, delta 103.1 is going to be equal to Q of 1 given 367 times T of A given and again we divide by star, the same sum. Delta 103.2 is going to be Q of 2 given 367 times T of A given, now we have the third word, we have the second word there, divided by star, and so on and so on. So we can fill in these values, delta 100.30, delta 100.31, delta 100.32, and so on, right the way up to delta 100.36. And you can verify that these different deltas sum to 1. So in some sense they're a fractional count. They say that, they sum to 1 and they define a probability distribution over the different possible alignments for this particular French word A. So these deltas actually have a very direct probabilistic interpretation, which is as follows. Delta Kij is the probability that the ith French word is aligned to the jth English word, conditioned on the English sentence EK and the French sentence K under my current parameters T and Q. So I'll write a semicolon here followed by T and Q to mean that we're talking about probabilities under the model defined by our current parameters. So basically what we've done in this algorithm is we've hallucinated these delta values by calculating probabilities of the alignments under the current parameters. And recall, we then use these deltas in calculating the counts which are used to re-estimate these Q and T parameters. So to recap, if we go back to this algorithm, again I'm going to show you this diagram just to remind you of this. We start off with some initial values for the Q and T variables, and we also have our data. So this consists of EK, FK for k equals 1 to n. From these two inputs we calculate counts, and these are often referred to as expected counts. And they're expected counts under this previous model, under the previous Q and T values. And we do that by using this definition of delta, which makes direct use of Q and T at the previous iteration, and we calculate the counts. From this, we calculate new values for the Q and T variables using these simple expressions down here. So that's the first iteration. And then at the second iteration, we repeat this. So again, we have two inputs. We have our data together with our current parameters. We calculate our expected counts. And from those expected counts, we re-estimate Q and T, and we just keep going with this process. And this is referred to as the EM algorithm, or at least this is an instance of the EM algorithm applied to these IBM translation models.